Turgeon here, bringing you physics from afar. This is about work and energy. This is about the equations. In particular, I want to give you some context behind them. Energy is useful. When you ask that, people say, oh yeah, it's useful because it gets me to school or allows me to eat, allows me to do things, allows me to speak, allows me to think. But I mean specifically energy is useful for solving physics problems. It's an approach. I won't be offended if you do any of these things. In the beginning of the unit, I started out with this example before you knew anything about energy. Now I'm going to use this as a context for the energy equations. Got a roller coaster going down a ramp, undergoes a lot of changes in energy. What do these things really mean? Let me tell you. The equation, U sub G equals mgh, anytime you see a U, that is a form of potential energy. Measured in joules. A joule is a kilogram meter squared per second squared. Think about it. This is mass is kilograms, G is meters per second squared, H is meters, meters per second squared times meters, and meters squared per second squared. Kinetic energy, you got kilograms times velocity, which is meters per second, but that's squared, meters squared per second squared. Joules again. Work, as we know, is force times distance. Newtons times meters. That's a kilogram meter per second squared times meters. That's kilogram meter squared per second squared. This is elastic potential energy, also known as spring potential energy. The K is the spring constant. Fill in this blank. Spring constant is K. K constant, K. The X is the stretch or compression. You'll notice that X seems to appear a lot as a displacement. It's also called the displacement. It's how much the spring was stretched or compressed. Those units are newtons per meter. It's how many newtons it takes to stretch a spring 1 meter. This should remind you of the F equals kx equation, and they are related. This is the force that's responsible for doing the work that gives the thing the potential energy in the first place. Look at this. P is for power. It's work divided by time. That's how fast you do the work. Larger time, slower power, even for the same amount of work. That's measured in joules per second, which is called a watt. Watt, work, what? No, watts is the unit, as in the wattage of, say, this light bulb. Watts. You can show that power is also something interesting. If you think power is force times distance over time is velocity. Power is force times velocity. That's really hard to interpret spatially. These are all the equations. This is what they mean, but you got to think of them in context. mgh. Oh, it's got to have h. It's got to have mass. It's got to be an object. It's gaining its potential energy because, here's the context, it's in a system, it's in a relationship, a physical connection between this and the Earth with a height. G being the acceleration due to gravity on Earth. And if you look at it, you can think of it as the work that's done. Kinetic energy is energy related to motion. So if the thing's at rest up here, it has no kinetic energy because it needs to have mass and velocity. Spring potential, you can see that the higher stiffness of the spring stretched a certain amount is going to have a lot more energy than a spring that's not very stiff. Or you can say a spring that's stretched a lot has more energy. It makes sense. Remember, it's also compression potentially. This was really about equations. But those equations don't really mean much unless they really serve as anchors for your mental model. You have to be able to look at an equation and it means something to you. It's a relationship, sure, but it's got to be a relationship in context. Just saying PE is proportional to G doesn't really mean anything unless you can picture a mental situation. I hope you learned some facets of physics. This is Turgeon bringing you Physics from Fun.